Ferraro, and this talk is about integrating applications the reactive way. So, who am I? I'm a software engineer. I work for that, and I work on open source projects, like mainly on the integration area, for example, Apache Camel. How many of you already know Apache Camel? Okay. Yeah, thank you. I'm working also on another project right now that is called Synthesis.io. It's a new platform for creating integration as a service. It's a project for doing integration as a service. It's open source, and we are working on it right now. I think we'll finish it next year, mid next year. I'm working also on many projects from the Fabricate platform. I don't know if you know Fabricate. It's composed of many tools. I'm one of the maintainers of the Fabricate Maven plugin to put Java application directly on OpenShift, and also Kubernetes client, Killian Cube, Kubernetes. So if you want to talk about that, just ping me after this conference, after this talk. So today, I will tell you something about Reactive. How many of you have already followed some talk about Reactive in this conference? Okay, not anybody, because yeah, you had Josh Long yesterday talking about Spring 5, and there was Clement Escoffier also talking about Vert.x. Yeah, I will start this talk with a different definition of Reactive. I hope you will like it, but it's my personal view on Reactive application. Then I will talk about integration. I will show you a demo done with the Vert.x, Apache Camel, and other stuff, and we'll talk about this back pressure stuff, of what it is and how does it affect integration. So let's start. So this is my definition of Reactive. Suppose that you have to solve this really difficult problem. Okay, this is a game, and you have a ball here, and you have a bucket there. And the problem is you have to put that ball into the bucket. You have to design an application to do this. Okay, how can you design an application that does this? You probably have infinite ways to solve this problem. Okay, you can just throw the ball. You can design a slot and then push the ball, and the ball will go into the bucket. You can design an helicopter, whatever you want. But I think that there are a class of solutions to this problem that you can call reactive. And for example, this is one solution that I call reactive. Imagine this in motion, okay? So there is the first ball that is, it is moving, and it is the first event, okay? And then the domino falls down, it is the second event, and then the second ball falls down. Then you have a kick, a series of punches, and at the end of the day, probably, no, I assure you that at the end of the day, one ball will fall into that bucket. So why do I think that this is reactive? Okay, I think that this is reactive because what I have done to write this application is to design a static schema, a schema made of inactive pieces. They do not have an engine inside, they just react, do something when something else happens. So an event creates another event, that create another event, that create another event, like in a chain reaction. And yeah, chain reaction is actually the name of this game from Disney. I never played it, but you may think that I am crazy. So if you have followed yesterday the talk with Josh Long, you may have seen something like this. This is reactive programming. So I have a stream, and I apply operators like map, zip, merge, filter on that stream. Okay. So, but what does it mean in practice? What is a stream? A stream is a pipe where balls can flow inside, right? And the map operation is just a box that applies a function, one ball in and one ball out. And the function in this case is changing the color of the ball, right? And then you zip here in the code, you see here with another stream. And the zip is just another box that takes one element from left, one from right, zip them together. You know, the icon of the WinZip is a press. Press them together and produce another stream. And then you merge here with the stream tree. You see it? The merge operator produces another stream. Then you have a filter operator that filter what is almost round, and put the result in the bucket. So that's why I think that reactive applications are more or less like that game. When I write a reactive program, I feel more or less playing that game, okay? Where you have to design the schema that brings the balls into the bucket, something like that. But by contrast, how is a trait-based application? Well, when I think to a trait-based application, I think to this. So, Super Mario Bros. I played yesterday Mario Kart on the ground floor. It's not the same, but yeah. You have a lot of moving pieces. There are bullets flying in the air, and Super Mario that wants to go fast in this case, but he has to wait because in the air there are a lot of bullets. There are the threads, other threads that share the resources with you. And so in a trait-based application, you have a lot of concurrence, the resource contention, you have to use lock, wait, and define, synchronization primitives. So if you say that kind of application from the performance point of view, you already see that probably the reactive way is faster. And actually, it was 6 years ago when a friend of mine came and showed me a benchmark that was setting at Node.js, JavaScript taken from the browser and put on the server with one thread on the browser, one thread on the server, one single thread, was faster than Tomcat even on a multi-core machine. And I said, how the hell is this possible? We have multiple threads in Tomcat. And you compare it with interpreted language having one single thread, and Node.js is faster. And actually, at that time, it was possible because Node.js was one of the first frameworks that used this pattern that is called the reactor pattern. Basically, you have one single thread in your application. This thread does always the same thing. You have an event queue or event stack, depends on the implementation. And the thread takes one event and executes the event handler, takes an event and executes the event handler continuously. The event handler can generate other events or do I/O, asynchronous I/O that generate other events. And like in a chain reaction, you know, an event that generates other events. Probably the reason why this pattern was called reactor pattern is because the chain reaction is what happened inside a nuclear reactor. Okay? So in JavaScript, you don't have synchronization issues because you have one single thread. If you look at modern implementation of this pattern, for example, the one in Vert.x, but also the other libraries that offer you reactive programming, you will see that if you have a machine with 2 cores, for example, 4 threads, 4 different event loops will be created. 2 times the number of cores on your machine. But even if you create more than one event loop in Vert.x, for example, you don't have synchronization issues because the vertical, that is the basic runnable object in Vert.x, every piece of code inside one vertical will be executed always by the same event loop. It doesn't change event loop. So you can use local variable, store variables, read and write local variables without issues. But actually, if you use a reactive framework, you should never use synchronization like thread.flip or synchronized block, do heavy computation, or for example call the JDBC, your database using JDBC synchronous API. You cannot do anything of this. So you cannot use the whole Java library ecosystem. Okay. Using the event loop, you should use the other threads. And if you block the event loop, one event loop, the other tasks accumulate and the delay will increase. So that's why you should never stop the event loop. Okay, this is a different perspective on what I'm saying, so I will go fast. This is what happens inside a reactive application. You have a machine with 2 cores, you create 4 threads. No matter how many requests are there, 100, 1,000, 1 million, 4 threads. Okay? And it's the reactive framework that schedules this request, this task into these 4 threads. But if you see a thread pool-based application, what happens in a thread pool-based application? It's this, that you create a thread pool composed of 100, 1000. It depends on the level of concurrency that you want to achieve in your application, right? So the difference here is that in this case, it's the reactive framework that schedules the task of the threads at the user level. In the other case, it's the Linux scheduler that schedules that threads one at a time into the machine code. And so the question now is, why do we think that we are better than Linux? Why do we think that we can do better than the Linux scheduler? Okay, I have a long answer to this question, but yeah, not today. I will show you just the result. The main reason, okay, one of the reasons why the reactive approach is better is that you have few context switch. When you do a context switch between two threads, basically you switch from user mode to kernel mode because the Linux scheduler runs in kernel mode. And you do this 2 times. Every time you switch from one thread to another, it's preemptive. And you lose a lot of time doing this continuously, especially when you have a lot of threads. The other big problem is the thread migration. Every thread in the Java virtual machine, but in any application, is usually bound to a core. And it is always executed by that core. But if you have, for example, one core that is executing a lot of threads, and it is high loaded, and there another core that is full of threads that are doing I/O. What the Linux scheduler does is move one thread from the high-loaded CPU, from the high-loaded core to the other one. Because the goal of the Linux scheduler is complete fairness. But this seems reasonable, but doing so means that you discard, basically, the L1 and L2 caches of the core. So it's where the thread have written the stack, the local variables, and what is being using. So reactive application use better L1 and L2 caches. And in case you are wondering, writing and reading data from L1 cache is 100 times faster than using the main memory. There are some benchmarks that say that you can gain 50% throughput using a reactive approach. Okay, but yeah, it depends on the application, you know, as usual. So when you want to use a reactive application, you cannot program like you always did in the last 30 years, 20 years. You have to use different constructs, different way. I call them flavors. So, and you have the functional flavor. So applying functional programming on on streams. And you can do it also in Spring 5, for example. You have seen it yesterday. The classical way, the one that was used in Node.js, that is still used in Node.js without promises and stuff like that, but it can also be used in Vert.x, is the callback flavor. So instead of calling a function that returns me a result, I call a function and pass to this function another function that will handle the result. And so on. You can go and you can reach a callback hell very easily with this model. So in Vert.x you can also use the functional flavor if you want. And there is one other flavor that you can use, and a lot of people like the actor flavor or the functional flavor. The actor flavor is basically what can be used in Akka. For example, you declare an actor that can, and you define what the actor should do when it receives an event. So changing its local state, sending other messages to other actors, etc., etc. So a different way to write your applications. And these are the main flavors that you can find if you want to write reactive applications. But there is another one. I'm talking about coroutines, continuation, pipers, async await. I don't know if you are aware of this. People started to find some ways to write synchronous code. So this is a variable, I read data from the database and assign to this variable, then I do this, I call the service and say that. So this is synchronous, blocking code. And it's the compiler that transforms this into asynchronous code. Okay? It's difficult to do it. It's not easy, but you have support for this, for example, in Vert.x, where you have async await. And if you follow this link, I will give you the slides. There is a presentation of Julien Vier that talks about how you can use these kind of constructs to also in Vert.x with Kotlin. Okay. Yeah.
I think with the Vert.x sync, there's also Flavours, which does a similar thing.
Yeah, but you have different things to do this. There are also other languages, for example, in Go. Yeah, you have that the Go, the main flow is not bound to a kernel thread. It's a Go routine. So yeah, different languages also have different way to handle this problem. That is what is going on in Java JVM based languages.
Right. Okay. I was just saying that in Vert.x you can also do it in Java.
Yeah. Okay. Yeah. Something like it. Okay. Let's talk about the other part. Integration. So far I've shown you that you have reactive has some different meaning depending on where you apply it. For example, at core level, using an event loop means you are doing reactive programming. If you're using asynchronous or reactive programming, at application level or not. But if you scale from the single application to many applications communicating, you have the reactive system. When you talk about reactive system, you're talking about a completely different beast. We're not talking about event loop and etc. etc. It's this definition of reactive system is a reactive system is a system that is responsive. It can react to user request. It's elastic. It can react to load, react to failures. It's resilient. And all these features are enabled by the main feature of a reactive system that is being message driven. So in a reactive system composed of multi-application, you communicate using message passing. With location transparency, I mean, I don't send message to an endpoint, etc. I send message to channel, topics, queue, something like that. And back pressure. We'll talk later about back pressure. Okay. So yeah, there are toolkits in the Java system to build reactive system. For example, Vert.x and Akka. I can tell you they are toolkits to build reactive systems. There are libraries to do reactive programming. RxJava 2, Project Reactor by Spring. I don't know how to classify all the other reactive stuff, but I don't think we have to. Okay, but just know the main two categories. This is an example of reactive system made with Vert.x. You have in this system two microservices and a browser. Okay, they communicate using this entity called event bus. The event bus is a logical entity. It's not a physical application. Okay, you declare on each microservice how to create this event bus, and it's composed of channels. So microservices can send messages to channel, and then the message will be received by the other end. And also this applies also to the browser part. So what about integration? Usually when you have a reactive system like this, the problem that you have to solve as soon as you start is that I want to use the data that is provided by another system. There is another team that is doing something else. I need to use that data. I need to call, for example, services exposed by the other system. How can I integrate this my reactive system with that? And yeah, best way to do it is build, for example, an integration microservice, put it into your system. For example, you can use Apache Camel for that. And this will communicate with the other system, no matter how it is implemented. And then you will communicate with that system using the structure of your system, so the Vert.x primitives, okay, in this case. And this applies also to other. The goal is to create a bigger reactive system. Integration. Integration is about communication, so passing messages, calling services, but also converting protocols. We'll find that any system, old or new, is developed using different technology because the technology evolves and everybody tends to use whatever they want to solve that problem. So integrating means also converting protocol, but also mapping the context. You have a domain model here, you have another domain model somewhere else. And integration, the role of integration is also to do this mapping bound the context, correlating messages, routing flow, control the flow. There is a book called Enterprise Integration Patterns, written by Gregor Hoop and Bobby Wolf, that talks about integration pattern. And actually, it has inspired the creation of this framework, what I'm working on, that is called Apache Camel. So Apache Camel as a library is part of a product that we call JBoss Fuse, and a lot of other products use Apache Camel as core. And it has more than 200 components. Yeah, you have them here. Okay. I applied to some of them that I like more. There is a component for JGroups or CXF or JMS or I don't know, MQTT, MQP, HBase, HDFS, whatever you want. You can connect with any system with Apache Camel, and contributing to it is really easy. So there are a lot of contribution by other guys. So Camel can be used really easily. You define routes. And routes is really similar to a string in a reactive program. You see here, I read from this URI, JMS, Q, named orders, then I log the message, and then I send to this service, and then I send an email with the content of returned by the service. 2 is more or less like a map operator on reactive programming. Okay, this is the way you program, you write Camel routes. And you can also do difficult things, okay, not so difficult. So read data from HDFS, do a complex transformation of Marshall, or split the body when you have an array or something like that, or a stream. Then, depending on the content of the message that you are receiving, do this or do that. So this is part of the enterprise integration pattern that you can do, but also something that can be useful. You receive a stream of the events that are not sorted with a from what resequence based on something. You can just sort the messages before sending downstream. And also, yeah, aggregations, and also routing based on the content, sending one message to the different endpoints. Try to do this with reactive programming and tell me if it's easy. Okay. And also more modern things like circuit breaking when you call other services. And you know what you probably know what a circuit breaker is, okay? Just if the service is going down, if the second service is going down, and I started I started to understand that it is going sorry, it's going slower, and started to send me errors. I basically break the circuit and stop calling it, give him time to recover. Then in the meantime, I'll send to the user something else. And then when the service, sometimes I try if the service is available again. When it is available again, I will call it. So give time to the other service to recover, and other stuff like that. Now the point. Is Camel reactive? Camel, I don't know if you've seen the slide before. Camel has been created 10 years ago. So nobody was talking about reactive. Nowadays, in a conference, you have 2-3 talks about, I've seen conference with 30% or 40% talks about reactive. Reactive programming in 2007 was not known like now. So, but Camel is not reactive, it is transforming. The next version of Camel will be Camel 3. We are we'll do a lot of effort to make it reactive, to give it a reactive core. But now it's not slow. You have seen before the thread pool based application, the thread pool model. Camel is not using that thread pool model. It doesn't need to allocate one thread for each request, because yeah, you have 200 components. Probably the old components use that model, but you have really many asynchronous components in Apache Camel. You can use Netty, I will show you how. And Also, the core is asynchronous, so you don't need to allocate a lot of core. It supports back pressure and throttling. They were called differently in a previous year. It was not called back pressure. We'll see what it is. But yeah, you can do a lot of asynchronous stuff also in Camel. The difference is that you will not have a number of cores that is the double of the number of cores that you have in your machine. You have to tune it in Apache Camel. Okay, but the performance will not be so different. Let's take a look at the time. Okay. How to integrate. So here you have a reactive system. This is a piece of your reactive system, reactive application integration services that we have created. And there is an external system that I model with a black box, of course. How can you integrate? As I showed before, you can put, for example, integration model inside your application, or we can build a service that does integration with your reactive system. But the problem is now how this integration module built with Apache Camel can communicate with your application, whatever. Nothing magic here. Okay, let's start again. And we will conclude with the back pressure. So I could have used also the Vert.x component. I showed you the reactive string components because I've made it, and that because it is more general and can be used also with other reactive frameworks, also with Spring 5. And back pressure. Who is this guy? So normally you have streams and you have operators and that produce other streams, and you subscribe to that stream and everything flows normally. But sometimes you have slow operators, or you do I/O, for example, with other system, and things can start to slow down. So here is the classical case of a slow consumer and a fast producer. The producer is sending messages and the consumer cannot keep the same pace. So what you do, you should communicate back to the producer that it should not send a lot of messages. And the producer should communicate back to the producer upstreams and the same information. So this is back pressure. It's like water in the pipe. You put a lot of water in a pipe, so you feel a pressure that goes in the opposite direction. That is why it's called the back pressure. And in reactive streams, the back pressure is handled this way. You have a publisher and a subscriber, and they are connected, right? And usually the subscriber subscribes to the publisher, and it receives a subscription. And with that subscription, subscriber can tell the publisher, you can send me one message. And the publisher, when it's available, will send that message. And then you can send me 2 messages. And then the publisher will send 2 messages when they are available. That's how the flow control works in the reactive stream classification. That's why it's difficult to implement that for interfaces. Okay? Because losing back pressure is really easy. So let's see a microservice architecture or a lot of services communicating. So in this case, we have this microservice 4 that is highly loaded. When the microservice cannot keep up with the load, what it does, it starts to time out, it starts to send errors. Okay? So what you do in the other microservice, for example, you can use Asterix usually, okay? Because you give time to that microservice to recover, and then you start to send message again. But if you had back pressure at system level, what you could do? You could do this. The microservice 4 cannot keep up the pace. Okay, so the back pressure is communicated back to the other microservice, and messages are, for example, here buffered at the source, where you have a lot of capacity. But yeah, probably you will not do that always, because here the latency is really high from the client to the first server, so the API gateway usually. So you probably would buffer the messages in a point in the middle using Kafka or messaging broker or something like that. So it's up to you, but with back pressure at system level you can do stuff like that. But how can you achieve this back pressure? Not in the same JVM with Reactive System, but between 2 JVM separated by a network. Upfront, there are some specifications. For example, this one socket. But wait. This back pressure stuff is not new, right? Do you know any protocol that implements back pressure? No? TCP/IP? In TCP/IP, the receiver has a window. You cannot send many bytes, more bytes than the size of the window of the receiver. So TCP/IP is back pressure away. We are doing always the same stuff, but with different names. Okay? So it's a known problem. Slow consumer and fast producer is a known problem that has been solved also at TCP/IP level. So one solution to this problem is this. For example, if you can control the TCP buffer, and you have a reactive application here, you should just not write more. If the TCP buffer is full, you should block the upstream producer. And in the other side, if the downstream consumer cannot keep up, you just should not read from the TCP buffer. And if you do so, you have a back pressure communication. But actually, in theory, this is easy, but back pressure is like teenage sex. Everybody talks about this, but nobody is able to do this. To bring that back pressure at low level, at high level. We do a different thing in Camel. Because, okay, let's see this case. Here I have a reactive application that is send message to Camel, and Camel will call another service. Okay? So we can tune in Camel how many messages we will like to have inside that the Camel route. It's like tuning the buffer size. And if you send too many messages, Camel will communicate using these reactive system components that it cannot keep the same pace. So with back pressure will be communicated back. Okay? It's not like controlling the TCP buffer, but it's almost the same. And you can also throttle. You can tell, I will not like to send more than 3 messages in 10 seconds to that service. And if you have a huge load of messages, Camel will stop it with back pressure. And in the other side, for example, if you receive messages from an asynchronous source like Q, Kafka, QTP, MQP, whatever you want here, and you have a receiver that is a reactive application, if that is low, the back pressure is communicated back to Apache Camel, and Camel will stop the consumer, stop reading from Kafka or the GMS queue. And then when back pressure says, when the consumer says, I can receive 100 messages, Camel will start again the consumer. This is how it works basically. And yeah, last but not least, you can do whatever you want with Camel. For example, putting a messaging broker in the middle, also to have location transparency when calling other services also. And in this case, you can have back pressure managed in both sides. And yeah, Kafka is also called anti-back pressure because if you have a lot of clients, one solution, if we have a service that is slowing down, is to keep the messages at the source. But if you have Kafka that can scale out to a lot of instances, you can just throw messages to Kafka and then read them again, avoiding the latency of the communication between the client application and the REST API gateway. Okay, I think this is the last slide. So, thank you. We'll put these slides on Twitter in a few minutes. So if you have questions, yeah.